Thank you. It's a pleasure to be here. Good evening. Albert Einstein once said that there were only two things that might be infinite: the universe and human stupidity. And he followed it by saying that he had no confidence that the universe was infinite. Now, when we hear that, we chuckle, or at least we smile. But what we don't do is, nobody feels insulted by that. No one takes offense at it. And the reason, of course, is that when we hear those words, right, we see Albert Einstein, right? We see that warm-hearted, that good-natured avuncular sage from an earlier era, right? We see the wild-haired, starry-eyed genius, right, whose iconic imagery from riding a bicycle to sticking out his tongue to being lost in pensive thought, all of this imagery is emblazoned in our collective cultural memory. And Einstein's story, right, at least the version that we tell when we retell, right, of the young boy who could barely talk until he was 3, 4, or 5, or the young student who failed at school, or the young, brash graduate who gets shipped off to the patent office. I mean, this is stuff of myth-making. And then the storm of creative thought that flows forward, that launches quantum mechanics, the special theory of relativity, the general theory of relativity, completely rewriting our understanding of space and time and matter and energy. I mean, as a physicist, I have studied these ideas intently. I've taught them. I've spent decades with colleagues trying to push these ideas forward. And I have to tell you that they never lose their wonder. I mean, I am as amazed today regarding what Einstein found as I was when I first encountered these ideas 30, 40 years ago. So, how did he do it? Right? Is it personality? Is it perspiration? Is it some potent mix of brain physiology together with the particular scientific moment when he came on the scene? Is it all of it? I mean, what was happening in Einstein's life when he was putting forward all of these amazing ideas, and how have his discoveries stood up to the test of time? Well, these are some of the questions that we are going to be exploring here tonight in tonight's program, a program that we at the World Science Festival are proud to co-present with the 92nd Street Y, and we are honored that tonight's discussion will be led by the senior legal and investigative correspondent at NBC News, the former anchor of ABC News Nightline, two-time Emmy Award winner. So please join me in bringing to the stage Cynthia McFadden. Great to see you.
I feel that we should have full disclosure. I come here as a journalist, which someone once said was just the little kid on the street who wanted to be the first one to run down the street and say, guess what I know? Well, tonight I don't know very much. I want to disclose that I had to drop out in college. I had to drop out of the class physics for poets, okay? I couldn't handle it. So I hope I'm going to learn a lot tonight. I certainly have a lot of questions. Brian, it's always great to be with you. And welcome to all of you to the genius of Einstein. I want to start with a quote from Professor Einstein. Here's what he said. I want to know how God created the world. I'm not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest are details. So tonight we're going to explore the genius of Einstein from three perspectives: who he was as a human being, what he scientifically gave to the world, and also what neuroscience may tell us about the man's brain. We brought together three people who have spent a great deal of time thinking about these things. You've already met Brian Greene, To talk about Einstein the man, I'd like to introduce author, filmmaker, and professor of science writing at MIT. He has produced more than a dozen science documentaries and written 5 books, including Newton and the Counterfeiter and Einstein in Berlin. Please welcome Thomas Levinson. Great to have you here. Also joining us is Professor of Neurology and Ophthalmology at Robert Wood Johnson Medical School of Rutgers University. His research areas have ranged from abnormal eye movements to the very brain of Albert Einstein. So please join me in welcoming Dr. Frederick Lepore. Dr. Lepore. Hi. So, let's get right into it. Let's start with the year 1905. It was known as Einstein's Annus Mirabilis, his miracle year. Brian, lead us off.
Yeah, no, that was an amazing period of intellectual fervor. It's hard to compare it. It's hard to even imagine that kind of scientific outpouring happening. So Einstein wrote many papers in that year. 4 of them were absolutely astounding. One of them did launch quantum mechanics. One of them established the existence of atoms. And the 2 that I think have captured our imagination more than any other were his papers to do with the special theory of relativity.
We're going to get into that more deeply as we go. But what was, I mean, to have this kind of a creative period, what was going on in the rest of his lifetime at that time?
Well, Einstein in 1905 was in some ways really disadvantaged, and in some ways, I think he himself would have said he had this great opportunity. He was disadvantaged because, for a variety of reasons, he completely failed to get the kind of university job or really entry into graduate school as it was then, not quite the way we do it now, after he finished his physics degree at Switzerland's leading technical institution, the Polytechnic in Zurich. And he alienated his professors. He didn't bother paying attention to things he wasn't interested in, all that, the kind of student you would expect Einstein to be. So he didn't get any help from them when he graduated, and he was in the wilderness. He taught algebra to high school students for a while.
That must have gone really well.
Can you imagine being Einstein's, saying, I couldn't figure out a quadratic equation under Einstein's tutelage? It would be very embarrassing. So he was disadvantaged. On the other hand, he got this job in the patent office where he was looking at technical material all the time. He was learning to visualize physical situations. And he had, partly because he wasn't really a great family man, he spent really a lot of time, even though he's married and had a young son, he had great freedom to just think. And I believe that one of the things you see in Einstein after he gets a patent office job and really starts settling into being a sort of grown-up, he really starts developing the characteristic he would have for the rest of his life, which was this extraordinary ability to focus no matter what was going on around him.
Would it be fair to say that his life was chaotic and that in his scientific life he was looking for more order?
I think it's certainly true, and Einstein himself wrote this in what he called his autobiographical note many years later. It's certainly true that Einstein saw in science an escape from, these are his words, the merely personal. There was this great territory out there. I don't think his life was terribly chaotic in 1905. I think he was a stolid, young bourgeois Swiss citizen going to his job every day, small child taking hikes in the hills with his friends. It was, Einstein, the young man, was not the bohemian, eccentric genius we later, as Brian was saying, we have this image of Einstein. Einstein at 25, 26 was a guy who went to his job and worked on his hobby in his spare time, and his hobby turned out to be revolutionizing the world of physics.
Hey, he did love to play the violin. And Fred, one of the things that you've learned in looking at his brain is you can understand some. Tell us what we can understand by looking at his brain. Okay, let's go that road.
He was a gifted musician, and he loved to play the violin, loved to play duets. And again, Dean Falk, who's the person who did the anatomy in a couple of papers, who I collaborated with, he has a finding of a kind of we'll show a picture of it later, but a knob. It looks like an omega sign, an elaboration of his motor cortex on the right side. And for somebody who's fingering with his left hand, we now know, mostly from neuroimaging, that there are a lot of musicians who do have this kind of elaboration in their cortex that you see with people who are left-handed string.
So does the knob predate being a musician, or does being a musician
question.
create the knob?
That's a great question. We don't know. We don't know. You know,
Come on, you're a scientist. You're supposed to know this stuff.
Well, you'd have to come up with serial neuroimaging for pure research purposes. You know, start with a 6-year-old, and it's a great question.
No one's done that? I mean, that seems like a scientific experiment you could do, no?
You'd need the funding. You'd need the funding. I mean, I hate to say, I hate to
There's
be
going to be a
crass
little cup
about this.
outside afterwards, yeah.
You know, you say, listen, I want to pitch this idea. Do 6-year-olds with cortical knobs become violin prodigies? You may be able to pitch that.
Or do prodigies develop a knob?
And it may be a little bit of both. I mean, I think if anything's changed in my lifetime in the conception of neuroscience is plasticity, that you can enhance your wiring by learning experiences. So the question is, if you spend that 10,000 hours or whatever developing a skill with your left hand, could you actually see tangible changes on the surface of the cortex? Don't know for sure. All we know is he had the cortical knob on the right of his brain.
Okay, so now I take a deep breath and I say to you, Brian, explain what special relativity is. This is easy for you and hard for me. Okay,
Yeah, so, you know, it's a funny thing because special relativity is one of the most simple ideas mathematically. It only uses high school algebra, but it is one of the deepest conceptual breaks. So it's hard for all of us to grasp these ideas. So roughly speaking, around the year 1905, a few years before, there was a lot of discussion and confusion having to do with light and its speed. And the question was, could the speed of light depend upon the source that's emitting the light, and could it depend upon the motion of the person receiving it, right? So if I was to take this coffee cup and throw it toward you at, say, 3 miles an hour, I won't actually, that's just a thought, a Gedanken experiment, as Einstein called it, right? So I throw it at you, 3 miles an hour, you'll receive it at that speed. It's obvious that if you run toward me, the cup is going to appear to approach you from your perspective more quickly, and if you run away from it, it'll approach you less quickly. And that is basic intuition about how motion works. But as it turned out with light, it seemed that that was not the case. If I fire a laser beam at you, it'll approach you at 186,000 miles per second, regardless of whether you're sitting still, running toward me, or going away. Now, at the time, many people were not ready to accept that kind of idea. They were coming up with all sorts of contorted notions to try to sidestep that. But Einstein was the kind of thinker who would just come out, see the facts very clearly, and throw away the preconceived notions and say, look, that is what is the case. The speed of light is constant. And you just need to accept that. The problem is, if you think about it, if the speed of light is constant, that means it's behaving weirdly relative to experience. And speed, what is speed? Well, it's how far something goes divided by how long it takes to get there. So it's space over time. So if speed behaves weirdly, then space and time are behaving weirdly. And Einstein went for it and figured out how weirdly they behave. That's what he worked out in special relativity.
Raise your hand if you could repeat that. No.
I don't know if I could repeat that.
So it's the relationship between space and time?
Yes, exactly. He finds that there's this kind of dance that space and time engage in, where they go back and forth between each other in order to keep the speed of light constant. And he makes that idea precise and mathematical. So if you want to figure out and have a sense of how this notion of constant light speed affects time, we'd love to use this little example here. It's called a light clock. This is really just like a wristwatch. It goes tick, tock, tick, tock. It's a way of measuring elapsed time where we can see the internal mechanism of the clock. You could use any clock that you like, but they aren't as transparent as this one. And for our purposes, you can use this to pretty quickly get to Einstein's conclusion, which is time slows down when a clock is in motion. Now, if you want, I can show you that, but I leave it up to you if you want to see more.
I say yes, yes.
All right, so
okay.
one piece of
You're not going to throw the
physics.
cup at me.
No, the cup,
okay.
well, I may throw it at you,
Okay.
but not yet.
Okay, good.
But so what we want to do is now take two of these light clocks, and we want one of them to move relative to the other. So the one on the right, we'll set it into motion. Here's the thing. Look at the trajectory of that ball of light. It's going on a double diagonal trajectory compared to the straight up and down trajectory of the clock on the left-hand side. Now, if the speed of light is constant, and yet for it to go tick-tock in the moving clock, it has to go further because that double diagonal is longer. Look at time on the moving clock compared to the station. If you could actually run that one again so we can just sort of see it in action. Watch the counter on the moving clock compared to the stationary, and you'll see that time is elapsing more slowly, simply because the speed of light is constant, but the ball has to go further in the moving clock to accomplish tick, tock, tick, tock. Longer trajectory, same speed, it will go tick, tock less quickly. Time slows down. That little demonstration Einstein made mathematical. Again, it's high school algebra. And that transforms our understanding of time. Before that, everybody thought from Newton that there's a universal clock out there that ticks off time second after second after second. It drags us all forward in time at exactly the same rate, regardless of what we do, regardless of how we are moving. But Einstein shows that if I get up and start to walk, my clock compared to yours, if you look at it, will tick off time more slowly. More slowly. Time is not universal. Time is in the eye of the beholder and depends upon the beholder's motion. That's crazy, but true.
Was this the beginning of quantum mechanics?
Quantum mechanics is a different story that we could get into. But that reaction is perfect. In 1905, he did this, and he did wrote the first paper on quantum mechanics, and they're completely separate.
Lay it on us.
It's crazy. Well, yeah, quantum mechanics is a whole different story. And just, in two sentences, it's a theory that applies to the micro world and starts with Einstein's paper, goes through a lot of development, but ultimately it gets to a place where we learn from the quantum laws that you can't predict definite outcomes in any experiment. You can only predict the probability of one outcome or another. You can predict an electron will be here with 30% likelihood, 20% likelihood here, 50% over here. That's a completely different perspective of reality compared again to the one that Newton gave us. Newton says, tell me how things are, and I'll use my math to predict how they will be in the future. And quantum theory says that's the wrong way of thinking about it. All you can do is predict the likelihood of one outcome or another. Again, a completely crazy set of ideas that are borne out by experiment. And yes, you follow the intellectual trail of quantum theory, and it smacks right back into Einstein's 1905 paper, which is the one for which he got the Nobel Prize.
Tom?
So just a couple things as grace notes to what Brian has said. First of all, the paper he's sort of skipped over a little bit on the existence and dimensions of atoms and molecules is, of the 1905 papers, the most cited. And the reason is it has the most direct practical applications. It applies to such children's questions as why is the sky blue, which actually Einstein answered in another paper in 1910. But it's also used for doing things like working out the mathematics of mixing paint. So this paper that often doesn't get discussed in sort of, because relativity and quantum mechanics are so important, was itself, this amazing result. But the other thing I just want to say is that Brian said that one of Einstein's gifts as a genius was the ability to look at facts for what they are and follow them where they led, even if they upset preconceptions that Einstein himself may have had. And this was true actually even within the quantum theory. I mean, it's famous that Einstein really didn't like quantum mechanics in its
Right.
fully developed form. But he didn't stop doing quantum theory in 1905. He kept doing major contributions to the quantum theory for another 2 decades. And he even did the first papers that really looked at the fact that in the micro world, you would have an essential irreducible element of randomness. He published this stuff started publishing it in 1916-17. And he wrote a letter to a colleague, I think it was Max Born, a close friend and a great physicist, Nobel Prize-winning physicist in his own right, and said, I wouldn't want to give up causality, but there it is. And so when you think about Einstein in his just the kind of mind he was and the kind of sort of attributes that made him so powerful a thinker, on the one hand, it's his ability to see facts for what they are, consider their implications, and follow them where they will. And it's notable that this wasn't, in some senses, an infinite resource. He was able to do it with the quantum theory for a very long time, and he reached a point where not just because he was getting older and less flexible, though that was part of it, but because, in some sense, he was also prone to thinking about things that were congenial to him. He had taste in physics. He had things that he liked. He had ideas he responded to more than others. And there was a point at which physics moved away from the center of his affections. But before it did that, and even after, he was still an incredibly formidable thinker, but before he did that, he was just astonishing.
I want to come back to the brain in just a second, but first let's go to Berlin. 1914, almost a decade after these amazing papers come out. The politics and the circumstances surrounding Einstein's life at that time. Let's talk a little bit, Brian, about how these circumstances affected his thinking and his productivity as a scientist.
Well, I think Tom can probably speak more to the surrounding influences, but Berlin was the time when he is hot on the trail of the general theory of relativity. He'd spent some time in Prague, moved back to Zurich, and then finally goes to Berlin. I think it was 1914, spring of 1914, he goes to Berlin. And he started to really think about general relativity back in Zurich in 1912 and makes some headway toward the general theory of relativity. But it's in Berlin that it really starts to all come together. And by 1915, November 19, we're in the 100th anniversary of that momentous month. He gives 4 lectures at the Prussian Academy of Science where week after week after week he's getting closer and closer and closer. And finally, November 25th, he writes down the field equations of the general theory of relativity.
So, Tom, set the picture for us. I mean, he is being wooed to Berlin, despite the fact that he's Jewish. Right?
Well, this is 1914. I mean, one of the things, just as Brian said at the beginning, we have this image of Einstein at the end of his life, and we sort of push that back to the beginning. We have this image of Germany in the 20th century, and the Germany of the post-World War I period and then the Hitler period is very, very different from the last days of Imperial Germany, which is what you have before the start of the war. So yeah, there was anti-Semitism all over Europe, but it was genteel anti-Semitism. And for Einstein, it really wasn't much of a it just didn't really register on him yet. He was wooed to Berlin in what was really a bargain. I mean, Einstein saw it that way. He was clearly one of the strongest, if not already the preeminent theoretical physicist in Europe. And Germany in general, and Berlin was the center of European science. It was, and certainly for physics. I mean, it was an amazing collection of people who were working in the Prussian Academy and the various institutes. So Berlin said, we want you to add luster to our establishment, and we will bring you there with no teaching responsibilities, a great salary, your own institute, support for things that you might like an expedition to test your evolving theory of gravity. Why don't you come? And he said, fine. Even though, among other things, his wife really hated the idea. It was, look, the idea of institutions wooing star academics is not exactly a foreign one. I mean, it does occasionally happen in this day and age. So, and that's really what happened. And I think Einstein had no thought of politics at that time. I mean, it's hard to recall how implausible World War I was up until, days before the declarations of wars were
Though
handed
he
up.
certainly became political. I mean,
Oh, he became political because of the war, not beforehand. It was explicitly the reaction of his fellow German scientists to the outbreak of World War I that first triggered his political instincts. There was this famous manifesto of '93, which 93 leading German intellectuals signed this document that said Germany is not to blame for the war. We are bringing civilization. We aren't as bad as the English and French who are allying with Mongols and Slavs. I mean, it was really horrific, and it was again, with hindsight, it looks, oh, of course they would do that. It's how German. But to Einstein, it was a complete surprise that his cultured, literate, poetry-quoting physics colleagues would join in this manifesto, and that they would express such nationalism when, again, science was his retreat from the merely personal. Science was something that was international or supranational. He hated that, and he became political almost from the first moments of the war.
So in this stew, out comes the general theory of general relativity. Go.
Yeah, no, exactly. And it really was the result, in a sense, of almost 10 full years of struggle to try to figure out the force of gravity. That's what the general theory of relativity is all about. And it's a funny thing to think about, because almost none of us today could even imagine spending 10 years on a single problem. I mean, you try to go back to get your grant renewed when you haven't got any progress on this problem that you set for yourself,
Right.
and it's not going to go particularly well. I mean, if Einstein,
It's like
can you
quarterly
imagine
profits
Einstein
for
putting in a
companies.
grant proposal and getting rejected, and this is the kind of thing that, at least today, would happen. So he had an amazing capacity to stay with a problem. And this issue of how does gravity work, that's really the issue that's driving him,
Right.
is one that he spends 10 years on, and finally not only comes to a beautiful answer, but he comes to a beautiful mathematical encapsulation of that answer. So what is the answer? Well, we all know that Newton basically said that you have the sun, you have the earth, and there's this force of gravity that keeps the earth in orbit. But Einstein was well aware, and Newton was too, that Newton's never told anybody how that force is communicated. So Einstein looks at this situation, as others could have done for 200 years. Nothing changed. Again, he just looked at the same thing that everybody else looked at. And so what do you have? You got the sun, you have the earth. What's between them? Space. So it's got to be that space somehow is the thing that communicates the force of gravity. So this little picture gives a sense of what that is. So here's 3D space, and Einstein's idea is that space is uncurved, it's kind of flat if there's no matter or energy. But if you bring in a body like the sun, Einstein tells us that the fabric of space, in fact, space-time curves, and it's that curvature that keeps objects in orbit. So look at the moon around the Earth. The Earth is warping the environment, and the moon is kept in orbit kind of because space is nudging it around, keeping it rolling along this valley in this curved environment. And if you pull back from this imagery, you see that the Earth is kept in orbit for exactly the same reason. That is what Einstein says is how gravity works.
And he didn't even have graphics. Think about it.
Yeah, I know. How did he even how did he do his public lectures? I don't know.
Wow.
True.
And the wonderful thing is, there is a mathematical version of this, which, again, this is the part that's harder to communicate if you don't study mathematics. But when we look at that equation, I wish we had it. I don't think we have it. But, it's this beautiful little equation. R mu nu minus a half G mu nu R equals 8 pi G over C to the 4th T. This beautiful little equation.
We knew that. Come on, Brian.
There you go. You give it back to us.
Right.
And when we look at it, it's one of the most amazing compact formulae that describes gravity in terms of warps and curves, the geometry of space and time. So many people look at this moment in November of 1915 as the pinnacle moment in Einstein's scientific career.
How can we know it's true?
How can you know it's true? Yeah, it's a good question. And for Einstein, we can answer it. For more modern things, it's harder. But for Einstein, he realizes that there are a number of ways that you could test this. The first is, in November of 1915, before, you can hold off on this for a second, he realizes that there's a puzzle, which I believe you just wrote a book about.
That's right.
And the puzzle is having to do with the motion of the planet Mercury. So people have known for a long time that Mercury's orbit wasn't closing on itself the way Newtonian physics said that it should. It was shifting by a little bit, 43 arc seconds per century, a little tiny shift. And no one could figure out why. Some suggested maybe there was another planet called Vulcan that was out there pulling on the motion of Mercury. And you have a beautiful book that's going to come out and tell people all about this. But Einstein says, that doesn't make much sense to me. Let me recalculate Mercury's motion using my new equations. Sits down, does the calculation, and by his own account, when he looked at the result, he had heart palpitations that lasted for hours because the math showed the same answer that the observers had. So that was a real key moment for Einstein. In fact, there's a quote, maybe you know what it is, but he says something like, "Something snapped inside of me." That was the moment when he knew that he had looked into reality in a way that nobody previously had. But a real test is not to retrodict, it's to predict something that no one has seen before. And that's where this wonderful little document that I think you brought to our attention, I never saw this before. It's a beautiful, can you bring that back up, that note? Maybe not. There it is.
There it is.
So, I mean, you want to describe this?
Sure. This is Einstein went through this enormous struggle to get to general relativity, and I will defer to Brian to tell me if this is true. But basically, as of 1913, he'd gotten some help with the math that was his mathematician friend told him was too deep and too hard for physicists. Grossman talked about the Riemann tensor. And
he said, physicists stay away from it.
Exactly.
And that led Einstein to look at it, of course. It was perfect.
And they worked out this amazing theory that had matter and energy warping space and time, except it wasn't, it was warping. He knew that time warped under gravitation at that point, but he wasn't sure about space yet. But he knew, even at that stage of the theory, that if you saw gravitation as matter deforming space-time, then anything that travels through space-time, including light itself, would be deflected in the presence of a big gravitational field, a big dent in space-time. And that's what he's drawing here. And what this letter is about is in 1913, he's figured this out. He's got a number. It's the wrong number, it turns out. He's going to work it out later. But he's sending a note to the American solar astronomer, George Ellery Hale, who, among other things, built the biggest telescopes in the world for about 30 years. But Hale was himself not a deep space astronomer, but a solar astronomer. And Einstein wanted to know if there was any way at all that you could actually test this out in daylight. And the answer was, Hale regretfully reported, no.
But it turns out that you can take this idea further, which Einstein did later on, and realize that during a solar eclipse, when the moon obscures the sun, you can see the distant stars, and according to these ideas of general relativity, the distant starlight should travel on a curved trajectory on its way to the Earth, being moved, deflected by the sun, and that would therefore shift the star's apparent position in the sky. So if during a solar eclipse you could take photographs of the background stars and compare their positions to where they appeared 6 months earlier, when the sun was on the other side of the Earth and having no influence on the trajectory of the starlight, a tiny shift would be apparent if Einstein's ideas are correct. It's a little tiny angular difference, but Einstein could calculate what it would be.
So that's the proof.
Well, that's the proposal. Then you got to go out and do the measurement. And the measurements were undertaken in 1919. 2 teams went out to Brazil and off the west coast of Africa, and they took these photographs as best they could. There were various technical problems with weather and so forth, but ultimately, by September of 1919, the data was analyzed, and the folks doing the analysis were convinced that the data established Einstein's theory. And they send Einstein a telegram, and Einstein sees that the result is positive, and he's with a student at the time when the telegram comes, Ilse Schneider, and she says to him, "What would you have said, Professor Einstein, if the results had not agreed with the general theory of relativity?" And Einstein famously says, "I would have been sorry for the dear Lord because the theory is correct."
Like how he thinks. So he was arguably the most famous, and is still arguably the most famous scientist, one of the most famous men to have ever lived.
And that's not a very high bar, we should say, but yes,
Brian
he
Greene,
is.
yeah.
No, it's
So I'm interested in how he saw himself at that point. And I'm interested in his brain. I mean, it's worth noting that Einstein actually had his own brain, had an EKG done of his brain.
Yeah, an EEG done of his brain. I mean, it's hard to translate the anatomy into the guy's personality, but the guy was saintly. He had, in the sense that he was very self-effacing. I mean, again and again, he had this incredible reputation, but he was not a hard bargainer when he came to the United States to work at the Institute for Advanced Study. And, you know, I think at the end, if you want to bring it back to the brain, one of the, you know, he was cremated, and I think one of the reasons he was cremated was he was concerned that people would want artifacts of a saint, and he was right. At the time of his autopsy, forget about the brain, his eyes were removed by his ophthalmologist, and they've never been seen again. And this was his own ophthalmologist, and he was dead on that.
I'm glad we don't have that picture, yeah.
Yeah, I don't have a picture of that one, sorry. But, you know, he was a very modest kind of a guy who lived in a world of ideas.
And yet, by the time he comes back to America, many people talk about these next 30 years as the lost years. And I'm fascinated by that. A man with this enormous brain who has these thoughts that are unimaginable for most of us, that are even proved, some of them
Well,
maybe not yet.
He never made his peace with quantum mechanics. He never made his peace with it. And
But what about those years, he gets lured to Princeton. Mm-hmm. So tell us about that.
Well, he became, you know, from his start in anti-war politics in Germany during the Great War, the Great War, you know, he went on to develop a much broader and I think more generally humanistic set of politics. And he was an acute observer of what was going on in Germany, you know, including threats to himself personally. I mean, he once said that he didn't know he was Jewish until his German enemies taught him. That's a paraphrase, but it was pretty close to that. And so he was attentive to the rise of Hitler. At first, like most sane thinking people, he thought Hitler didn't have staying power. He said, you know, Hitler's risen to power, again a paraphrase, on the empty stomachs of the German people, and you know, when things get better, he'll disappear. But by the 31, 32, it was very clear to him that that Hitler was a deep and immediate danger to Germany and to Jews in Germany in particular, and that it might not be tenable for him to stay. And at that point, he had already a deal with Caltech to do a 1 semester a year for 3 years, a visiting professorship. And so he was coming to America every year. And I think, you know, by middle of 1932, he was thinking that he might not come back from his next visit to Caltech. And it was in that circumstance that Flexner, the magnate the intellectual impresario who set up the Institute for Advanced Study, decided that he would try and bag the most famous name in science to put his brand new institute on the map. And he made Einstein an offer, and I think Caltech expected to get him and were surprised when they did not, especially to, you know, the Institute for Advanced Study now is this extraordinary place with this great reputation and all these people who've been there. But then it was an empty field in Princeton, borrowing quarters on the campus of the university there. It was nothing. It was just starting. And it was, I think Einstein at that point though he'd been very worldly and very much involved in big city affairs, I think he actually welcomed a chance to get away from the craziness of Europe and go to a place that he had his doubts about, but that was, he called Princeton a land of puny demigods on stilts in a letter shortly after he got
But
there.
why Princeton over California?
I think he liked the peace and quiet. I think he liked, in some senses, the isolation. I think he was beginning to really value both an ability to focus on what he was interested in and perhaps some remove from a physics community that was no longer interested in things that he valued and that he correctly saw as less and less interested in his view of the proper path for physics going forward.
So is it fair to say, Brian, that he was less productive during these years?
Oh yeah, hugely so. I mean, between 1933 and when he died in 55, he wrote a lot of papers. But the ones that we really remember, there's just a small handful of them. The one that you referred to earlier, his work that was aimed at trying to use the math of quantum mechanics to destroy quantum mechanics in some sense, but ultimately it didn't turn out that way. In fact, he just revealed and emphasized one of the total strange features of quantum mechanics called quantum entanglement. That was 1935. He wrote some other interesting paper in 1939, but throughout it all, he was in search of one real prize, which was the unified theory. And this was a direct extension of everything that he had achieved as a young man. So remember, back in 1905, he's in the patent office. He is an outsider to the establishment. Comes up with these new ideas of special relativity which turn everything on its head, and then he gets brought in to the establishment, but he's still a very independent thinker. 10 years later, the general theory of relativity, an amazing discovery. But now he's like smack in the middle of science in the traditional established sense, and it's as if at that point he is trying to use all of the techniques and methods that served him so powerfully well as a young man, and he just beats on that same approach over and over again, but the methods were no longer suited to the next task. The next task required other ideas, and that's why he kind of doesn't make any progress, really, toward the unified theory.
So I want to go back to the idea of genius.
Mm-hmm.
Was he a comet who flared out after 1905? I mean, was this because his brain, he overdid it and now he's resting? Was it because what? Or, does the human brain only have a certain capacity and he used it up and then some? What?
Well, I think scientists such as Einstein, and mathematicians in particular, they do have a trajectory, and they tend to have their greatest achievements earlier in life.
Why?
Flexibility, maybe, or it's hard to absorb the newer ideas.
We like to think none of that's really true.
Well,
that
also-
you can continue on for a very long career, productive.
All right, but isn't yes?
Let me just jump in here. Recall Einstein starts doing interesting publishing, and he actually published his first papers in 1904. And they were once dismissed as completely inconsequential papers. They're not. They're building blocks for some of what he's going to do next. And he keeps on doing really first class, Nobel Prize or near Nobel Prize quality work until 1925, when he is 46. Is that right? Something like that.
Born in 1879.
Yeah, so,
yeah, sure.
So he has a 20-year run of producing, bleeding edge stuff across, again, as Brian said right at the outset, his last papers were about statistics, and statistics in a very deep and important way that really were. He knocked right on the door of the modern quantum mechanical theory with that stuff in 1925. It's amazing stuff. He made a prediction that was only actually developed in those papers. That's where he predicts Bose-Einstein condensate, which is this new state of matter that happens when you get things very cold. And sort of quantum scale objects stop behaving like quantum objects. They become macroscopic objects. These are amazing, weird, difficult ideas. They involve leaps from mathematics to imagination about actual physical intuition. It's extraordinary stuff 20 years after he did the stuff that we started out talking about. So it's not as if, he flamed out after one great year. He had a run that was better than almost any person can hope.
Okay, granted, but does it still run out? I mean, I guess that's the question about genius. I mean, it doesn't.
Does it peter out, or did he finally launch upon a problem that was insoluble, which is the theory of everything? I mean, there's people, Witten at the Institute, they're still trying to suss that out with, unverifiable results. So he may have finally bitten off more than he could chew. No shame in that. But he did not, to his dying day, he was not able to come up with a unification of strong force, weak force, electromagnetism, and gravity. It was not going to happen. And he was sort of marginalized because of the quantum mechanics story. He never could accept it. He would get into fights with Bohr, and he would say, this is an incomplete description of reality. He just never could deal with quantum mechanics, and they marginalized him. So I don't know if that's, you're running out of neuronal steam, or you're picking fights that you can't win.
On the other hand, he becomes like this folk hero legend symbol, right? While he may not have been as productive, and I think we all have to agree, he wasn't as productive, right, as he was in his early life, he became this iconic figure. Show the picture of the sandals. I love this picture. Got the picture? There, it's coming. There we go.
Yeah.
Okay, who can't love this guy? Those are actually, now we know from excellent research that he is actually wearing sandals that are a woman's size 11, as confirmed by the man who sold them to him, David Rothman in Suffolk County, Long Island. We had to get that in.
But this is actually a kind of a tradition among physicists.
Is that what you look like on the weekend? Yeah, right. There you go. Nice. Yeah, good. Good luck.
Take that down now. Thank you.
There's so much.
Those are your shoes, young lady, right over there.
Yeah. Hi, Tracy. There is so much folklore around Einstein. I mean, I love the clipping from the New York Times where he says he's incapable of doing his taxes because they're so complicated. I mean,
and
political
he
comment.
cultivates that too. I mean, you've
Right.
studied this more than I, but he's well aware of.
There you go.
Yeah, there you go. He's well
Try
aware
filing
of all
that on
these
April
issues.
14th. Yeah, right.
And I think he enjoyed starting the myth going forward.
Yeah, so he kind of enjoys being a celebrity, right? I mean, he's no Kim Kardashian, but he's enjoying being a celebrity.
Well, he didn't do
Does
book
he?
signing tours, but there's lots of kids in Princeton probably still alive who he helped with their math problems. He was this kind of avuncular, as you say, genial person. I guess he did, that's obviously Charlie Chaplin, and he would take an occasional star turn, but he never really left Princeton from 33 for a prolonged period of time.
Yeah, that's the premiere of City Lights, and there's this famous, probably apocryphal story where, Einstein and Chaplin come in on the red carpet, and there's this crowd cheering, and Einstein says to Chaplin, allegedly, "What does it all mean?" And Chaplin says, "Nothing." Which again is, that story itself is part of the cultivation of the myth, the otherworldly man. Yeah, he did like being a celebrity, but he also used it. I mean, he actually made practical use of it. One time when he came to America, he made reporters who wanted to interview him make a small donation to help with one of his causes. I think it was displaced refugees. He obviously used his celebrity to do all kinds of attempts at political activism, including writing to Roosevelt that it was time for the U.S. to start paying attention to the atomic bomb. So I mean, he was willing to be famous if it helped him advance causes that he believed in, including that one.
So do you think it's possible he was distracted from the science or not?
I don't think we're going to know for sure. He certainly was on the larger arena in terms of being asked to be the prime minister of Israel or the leader of Israel at one point. That was
Which he turned down.
He did, to his everlasting credit. He had a wisdom.
And Ben-Gurion Ben-Gurion invited him to be president, and then said to an advisor, "What do we do if he accepts?"
Right, but he was a private intellectual. A lot of his work could be done by himself in his office, and he lived in a world of ideas. I think the thing that's often underplayed is the years at the Institute for Advanced Study. One of his boon companions there was Kurt Gödel, you know, the author of he framed the incompleteness theorem. So you've got Einstein with relativity, Gödel with incompleteness. The only one you're missing is Heisenberg with uncertainty, if you're talking about three kind of cardinal cutting-edge conceptions that characterize the 20th century. So God knows what kind of conversations he would have. And there's pictures of him and Gödel going towards Mercer Street for lunch. And I imagine he got his intellectual rocks off with some of those conversations.
I want to talk about it. I want you to talk about his brain and what we know actually physically. What do we know from Einstein? So you need to tell the story about what actually happened for those in the audience who.
Well, you know, cut me off because it's a long story, but it begins. The story of the brain begins when he passes away on April 18th, 1955. He knew he was going to die. He'd actually been living on borrowed time. He had an aortic aneurysm, abdominal aortic aneurysm, and you didn't have much you could do for it in those days. He'd actually had an operation several years earlier. They would wrap cellophane around it with the idea that you'd scar down to keep it from rupturing, but it didn't hold, and it came back, and he knew it, and so April 18th, 1955, he passes away, utters a few words of indecipherable German. We don't know what he said, and the body is taken down for the autopsy, the routine postmortem to determine the cause of death. And
now, had he left instructions?
No, nothing. There is nothing in the will about the disposal of his body. Somehow it was known, though, he wanted to be cremated. That was known. April 19th, which that thing you just showed, was the next day in the New York Times. His family, basically his son Hans Albert and his executor Otto Nathan, read that the brain has been kept. And they're going, what? Nothing mentioned in the will, but that was like not on the script. And they go to the pathologist, Thomas Harvey, a guy in his 40s, who's the only chief pathologist at this little little hospital, Princeton Hospital. And Harvey pitches the pitch of his life, and he says, we're never going to get another chance like this. Let me study the brain. And Hans Albert goes for it, and so does Otto Nathan.
So what do we know? What do we know as a result of preserving?
I mean, I can show you some pictures.
Let's do that.
Okay. Let me tell you what we don't know.
We'll start, okay.
Okay, it's not a bigger brain. It's not a bigger brain. Okay, that's,
It's not bigger.
It's not bigger. It's 1,230 grams, not a big brain. So if you're into the bigger is better, it doesn't work for central nervous system. But the architecture is different. And rather than me say, well, this squiggle goes there and that squiggle, let me show, okay, all right. So let me just orient you real quick. Cut me off if this goes too long. Okay, frontal lobe, that's the back of your brain. This is his right hemisphere. Right there is the split, the hemispheric split, inner hemispheric split. Okay, just the highlight, the game highlights on this. Okay, here's your frontal lobes. 1, 2, 3, 4. 4 frontal gyri. The great majority, of us have 3. He had 4. That is a serious anomaly. How do we know that? Because there are standard atlases of brain anatomy, Ono and Connolly. And again, I am stealing from my colleague Dean Falk, who's the real anatomist in this, and she pored over this brain. But in any event, that is not standard issue, that frontal lobe. Okay?
So
all right.
One more makes a big difference. Okay, got it.
Yeah, I mean, that's if I say anything more than that, you're going to say, well, you're a phrenologist, and I'm not. All I can tell you is the brain is different, and the guy was a genius. That's all I can tell you.
That's not going to get you an A on the final. Okay, go ahead.
I know. I'd love to say. Okay, all right. There's your cortical knob, the violin part. See that looks, oops.
Yep.
Oh, can you go back one?
Yep.
Give me a little more back.
One.
Okay, yeah. See that thing? Cortical knob. That's on the right hemisphere, so that's presumably.
What's the knob?
Well, call it an omega sign. Call it a kink. The literature calls it a knob. You see, it's that little, I'll show it to you better, but that little U-turn there?
Yeah.
That's not standard issue. And there's stuff we don't even know. This is a diagonal sulcus. Here, there's no name. I talked to Dean Falk, emailed her this morning. There's no name for that thing. It's not described in regular anatomy textbooks. So he's got a lot of variant anatomy. Next slide. Okay, this is if you cut the brain in half, okay? All right, so that's the frontal lobe, that's your occipital lobe, that's your corpus callosum. That's the fiber pathway that connects up your right hemisphere with your left hemisphere. We didn't do it. We recovered this photograph. These photographs have been lost for half a century. We recovered these photographs, and now we start to analyze them. And Dr. Men, Wei Men out in East China Normal, sees the photo, goes, wow, look at that corpus callosum, sets up a computer program. He's got a larger than normal corpus callosum. Large, not for age-matched guys, but for even young people. He's got greater internal wiring anatomically with his corpus callosum, which opens up a whole other can of worms where you're not really talking about the stuff on your surface, on your cortex. You're talking about the internal wiring. And he obviously, this is a sign of greater white matter internal wiring, or if you want to use the sexy new terms, connectome. He has a different connectome. That's the major finding on that.
So his brain really was different than everybody else's.
No doubt about it. They don't publish this stuff in Brain unless you can prove that it's anatomically very different.
So does the brain change over time with use? I mean, did he have an extraordinary brain and then, I mean, obviously the brain by itself, right?
The answer is yes, it does change, but you don't see it like this.
You don't.
I mean,
so this wasn't just because he worked really, really hard.
I mean, we don't know. First place, I got no cohort of genius brains. We're never going to get Newton. We're never going to get Galileo. We're not going to get Turing. So we don't have comparisons. We have some smart people, but we don't have Einstein quality brains to compare to. That's a problem with this. But if your question is, does your brain change with experience? Yeah. That's how Eric Kandel got his Nobel Prize. Only he wasn't working with human brains. He was working with sea slugs. And he showed that every time you shock these things, that they would rewire their nervous system. Now, the question is, if you multiply that by 85 billion neurons, which you and I all have, could you actually change the surface of the brain? I doubt it, but I don't know. You know, you'd have to have, you know, serial neuroimaging looking at cortical anatomy. And, you know, Dean and I, we basically, this is unfundable stuff. It's really cool. But I don't know if there's someone out there who could actually trace neuroimaging to show you, development of your gyri and sulci, your cortical anatomy. It's not out there yet if someone's doing it.
JB asked about the number of convolutions. I don't even know what that is, but thank you, JB. In the context of what are the physical manifestations of intelligence in the human brain, the size he asked about, and the number. What the number of convolutions, is that the squiggly thing?
Yeah, right, exactly. We call them gyri and sulci, but you know, it's not so much that it's a quantitative thing that, you know, I can show you that he's got different variant arrangement of
These guys.
Yeah, okay. This is his left hemisphere, and again, different stuff. This is your motor strip. That's your sensory strip. That's where that would represent your face. We know that because from cortical stimulation things, experiments, Penfield since the 50s. That is a very large, elaborate motor and somatosensory cortex around the face and mouth. But you can't translate that into special relativity or to quantum theory. He's got, this is Broca's area, his speech area. Remember, it's your left hemisphere. Very, very additional. You can't really measure that with a number, but he's got very involved cortical development there. You don't normally see that. So that's a variant. Here, one of the things we got into in looking at the old literature was the reason we were able to come out with this. I mean, people have had these photographs, but no one had dozens of these photographs. And the thing with the brain is you got to have it from different angles, or you're going to miss a lot of nuances of the anatomy. And to show you what I mean, the original articles in the 90s they said that this was a continuous groove, sulcus, and it's not. That is actually an interruption. That's an anatomical difference. That's a hidden gyrus. Now, if you take that photograph from another angle, which other investigators, they only had 5 photographs to work with, you don't see it. It's like a slot canyon. If you're off on the side, you can't see what's the bottom of that canyon until you get over it. And when you get that right shot, you see, where did that come from? That's a whole different gyrus hidden in that sulcus. No one knew about it because those photographs had been stashed in Thomas Harvey's cellar for a half century. So there's a lot of little things like that that tells you the brain is different. I just can't point to you and say, well, this is why he was a good violin. Well, maybe a violin player. Maybe I could tell you that. But I can't tell you why he could do Gedanken experiments. I can't tell you why he could learn tensor calculus to figure out the theory of general relativity.
Right. Why this brain leads to him becoming the physicist of the ages. I mean, you can't just, we don't know.
I mean, if you put that brain in front of me, you couldn't, or brains like that, you couldn't tell that the guy was, you'd say, well, that's an interesting brain. Part of the thing is this is kind of a lost art. You know, cortical anatomy is, this study was a very interesting detour off the main road of neuroscience, but it really is a detour. Thomas Harvey, the guy who did the original study and chopped the brain into 240 sections, and you'll see pictures of that, he didn't bet on this. He took the photographs because he's an obsessive, good pathologist, but this is where he thought the money was in terms of making a finding. You basically cut the brain into 240 sections, and then you make slides from that, and you look at the microscopic anatomy. That's what Harvey thought. If I can look at the microscopic anatomy, I can figure out what makes Albert Einstein tick. 30 years went by before the first paper came out in 1985, Marianne Diamond, and she said, well, maybe there's a few more glial cells and neurons, and they're still brooding that about. But 30 years, and he sent this brain around to the great neuroscientists, pathologists, such as they were in America. No one could find anything positive. Diamond does it in '85. 10 years later, there's one more paper on histology. So everyone, Harvey included, was focusing, it's got to be microscopic. And we just happened to get these photographs and said, well, let's just, for the hell of it, look at the surface of the brain. And in point of fact, it was dramatically different. Big surprise.
Well, I learned something. I don't know about the rest. Wow, okay. Good. So it's not size, we got that.
Yeah, not size.
But the physical structure is very different than a regular brain.
Absolutely.
Okay, thank you. Okay, but I mean, that's fascinating. And chopping it up really wasn't the key to it. It was looking at the whole surface of it.
Not the key now. I mean, if you're saying, if you say, well, Lepore, come on, you know, where do we go next? Can we look at the wiring? Can we look at the connectome? And now you're going to have to resection those cubes. They're embedded in plastic. Look at them under a microscope and measure the myelin length and of the neuronal fibers. Maybe you're going to get something out of it. I mean, the cortical anatomy, I think we've run the table on that. I just don't think we can go further.
It's a very interesting idea, though, that the brain itself doesn't make the genius. Maybe it's a necessary and sufficient condition, but then he has to do something. I mean, right, Brian? I mean,
yeah, I mean, it could be a necessary condition, but not
a sufficient condition.
Yeah, I mean,
right?
all the other things that were going on in his life. I mean, the things that made him look at the establishment and be willing to challenge it. I mean, the traditional graduate student goes up the ranks and wants to please their advisor, wants to please other faculty members, because they know they're going to give their recommendations for the next stage of their career. And Einstein just didn't care about that. And I'm sure you can trace that psychological mindset to earlier places in his life. People have done that. But I think that experience and that frame of mind was as potentially important as the extra thingamabob that one found inside of his brain.
That's what I call it, too.
Yeah.
I just want to bear down on this point a little bit, though. I mean, there's the father of quantum mechanics who turns his back on it, right? To those who have said the last 30 years of his life, not that they were unproductive, but not as productive. I mean, where do you come out in this conversation? How great was his contribution, in your opinion, after his arrival in Princeton?
I guess the answer is similar to Tom's, that in the grand scheme of things, it just doesn't matter. What he did by 1915 was so extraordinary that there's nothing that could possibly tarnish his standing in the scientific world. Now, it is the case that he had a singular goal and a singular focus, and in fact, he thought repeatedly that he had found the unified. He published many papers on the unified theory, and paper after paper after paper. Ultimately, he'd say, that's not quite right, but I have the new idea, and he'd publish that one, and this cycle went on for decades, and it ultimately was not influential. But he said, in other words, when we do our work today, day to day, there's almost nothing that we do that doesn't come to us from Einstein. Every calculation that we do relies upon ideas in relativity, either the special theory or the general theory. And every calculation that we do in quantum mechanics ultimately goes back to the very ideas that were in the photoelectric effect. So his influence is so spectacular and deep.
So, Tom, was he happy with himself? Did he feel he'd done a good job? How did he feel? Was he frustrated? Or did, you know, I asked Meryl Streep once when she was having a bad day, if she thought, well, I am the greatest actress of my generation. She said, do I look crazy to you? So how did Einstein feel about his accomplishment? Was he?
I don't think, I mean, I don't think most of us, most days take stock of our lives and say, okay, I am, you know, my life is a success, my life has value or not. Einstein, you know, Einstein did calculations on the last day of his life, right? Correct. He kept working. Mm-hmm. And I think that's, you know, he did say once that he knew that most of his colleagues thought he'd gone crazy. There was some, he put it slightly differently, slightly less harshly, but he says, but it's okay. I've earned the right to be as, you know, stubborn and as focused on what I'm interested in. And so to that extent, yeah, he knew he was Albert Einstein. He'd done good stuff, and if he thought something was important, it was okay to pursue it. But you know, going to the general
But did he see it as a failure, not being able to find a unifying theory of everything?
Yeah, I mean, yes. He yes and no. He, in the 50s, a few times said, you know, it's getting clear that I am not going to solve this problem. But he also said, I'm not going to stop working on it. This is the problem I'm interested in. Mm-hmm. You know, to the general question of, you know, what can we say from a singular, you know, one data point, Einstein, about the nature of genius? One thing is there is, you know, people are not geniuses out of context. Einstein, for decades, had a series of problems for which his experience, his approach, his aesthetics, just his, you know, what seemed to him beautiful, matched the problems that were in front of him. And when you had the quantum mechanical revolution, two things happened. One is that was no longer the case. This didn't meet his aesthetic interest. And also, to a certain extent, his approach, you know, leave aside his taste, his approach was no longer really suited for that. You know, the ways he thought of it, and this is, you know, I want to sort of toss to Brian, but, you know, his Gedanken experiments, his ability to construct very simple visual pictures that would allow him to abstract down to the critical problem, all that, that's, from what I understand from talking to people like Brian, is really difficult, as in impossible to do in the counterintuitive world of quantum mechanics. So the genius that Einstein was a great genius for that transitional period in the early 20th century, and not so much after.
Do you agree?
Yeah, no, it's true. I mean, and I think that if you trace the roots of that, you can find it starting to occur in the last couple months as he's trying to get the general theory of relativity. So he had this uncanny ability from sort of 1905 up to, call it, you know, 1912, 1913, where he would come up with these thought experiments and think them through and have these visualizations. But that in 1912, 13, leads him down the wrong trajectory. So he spends 2 years, roughly 1912 to 1914, on an approach to the general theory that ultimately fails. And at that point, he takes a step back and says, let me just let the math take me to the promised land. Mm-hmm. Let me just use Riemannian geometry, tensor calculus, and I'm going to follow it where it takes me. And it leads him to the answer. And I think from that, he kind of changed his approach, where now mathematics was going to be what would lead him forward, and a very particular kind of mathematics, a mathematics that's much better suited to the classical world, that's not suited to the quantum world. And I think that is why he goes like this after sort of 1915, 1919, following that same kind of mathematical trajectory that had been so effective. Mm-hmm. But it no longer was the right approach. So even regardless of the folds inside his brain, he had a style. He had a belief in the way forward. But it turned out not to be the right one. Or not yet. Who knows? We don't have the answers yet. Maybe a generation or two from now we'll look back at Einstein and say he was actually following the right trajectory, but he just didn't get there. That could still happen.
So we have some great questions from the audience, so let's try to get through a few of these in our remaining moments. Why do you think Einstein never came across string theory during his quest for a theory of everything?
I just wasn't smart enough, you know.
Next,
missing a few folds.
They believe it. Right. Which of his discoveries did Einstein like or enjoy the most? Great question.
What was this?
Which of his discoveries, his theories, did he personally enjoy or celebrate himself the most?
Right after November 1915, he wrote a letter to, I think it was Arnold Sommerfeld, great physicist, said, "Study these equations well, they are the greatest accomplishment of my life." As against that, he also said, "I spent much, much more time through my life thinking about the problem of the quantum than about anything else."
Yes.
So, maybe he's like a parent. All his children are beautiful.
There you go. All right, another great question. Do you believe that going through and learning to overcome adversity is key to accomplishing the feats that Einstein and other geniuses did in his life, their lives? Is there a neuroscience to support this?
Well, it's hard to reduce it to the neuroscience, but when you get back to general relativity, I think Einstein was a great intuitive physicist. I mean, with the Gedanken experiments, I'm in a box and it's accelerating, and is that gravity or is that acceleration? But at some point, he would take the bit between his teeth and say, I gotta learn the math. And he didn't like math. He felt to purely concentrate on math would take him places he didn't want to go. But in order to justify those physical intuitions, Gedanken experiments, then he would learn Riemannian. Then he would learn tensor calculus. So that's kind of like, if you're a research guy, you got to get a whole new set of skills. You got to build up your expert knowledge system, and you basically leave one thing and you have a whole new skill that you have to adopt, and that gets harder. I know it gets harder for me when you get older to learn a new skill set. But he could do it. He could do it. At a certain point, maybe he couldn't do it. But he had a great run. What do you compare him to? Isaac Newton? After Newton, when he left Cambridge, when the plague was coming through, and he goes off in the countryside and does calculus or Principia, what did he do afterwards? He ran a mint. He wrote things about alchemy. He had theological interest. But, it's just hard to have peak performance for clicking off those decades. So no shame in that.
And the hair.
The hair.
This is a little off
Newton
topic.
had great hair too, by the way.
Maybe we're finding a theory of everything.
Okay.
This is a little off topic, but I think, Brian, this is a question you might well enjoy. What will be the next significant breakthrough in physics?
Well, I think the big breakthrough is still finding Einstein's dream of this unified theory, but a little bit more specifically, Einstein gave us a new picture of space and time. Special relativity, we learned that they can sort of meld together, that motion through space affects the passage of time. In general relativity, we learned that matter warps and curves space and time in the surface of gravity. But there hasn't really been the next step in that progression, which is to address the question, what actually are space and time? Are they fundamental constructs, or could it be the case that space and time are themselves made of something finer, right? I mean, you look at any piece of matter, it's made of ingredients, molecules, atoms, subatomic particles. Could it be the case that space and time also are subject to that kind of structure, that there are atoms of space, atoms of time? What would those be? What would describe them? How do we describe a realm in which familiar time has not yet emerged because those constituents haven't arranged themselves in a manner that yields space and time as we experience it? So I think really getting to the bottom of what space and time are is the next big step, I think. Maybe.
That's pretty good.
I was going to say that. So I do think listening to you, listening to all three of you, I mean, in a way, there's also, there's a sort of science, a purity of science, but there's also a philosophy that goes along with some of this. Einstein referenced God a good deal. Let's talk for a moment before we conclude about Einstein's vision of religion and the greater whole, and how his ideas connected to that.
Okay. Einstein was an extremely clever man as well as being a deeply smart man. And he used God talk in a variety of metaphoric ways. He himself said that his God was Spinoza's God, the abstract ordering of the universe. He was not a person of traditional faith in any of the revealed religions, Judaism as his tradition. He didn't, the traditional view of God as some supernatural being acting in time, that was nonsense to him. And he could be very harsh in private describing this nonsense. He went to Palestine as then in the early 20s, saw traditional Orthodox Jews praying at the Wailing Wall, and was contemptuous of them. I mean, his private writing about it is just, it's really, these people are crazy. They're lost in time, this kind of thing. At the same time, he really did feel a very strong sense that the fact that the universe was ordered and that order was accessible to human reason was a deeply beautiful, deeply mysterious fact of life, right? And he was perfectly willing to talk about that in terms that were congenial to broader discussions about religion. So he used God in lots of different settings. He used the word God and the concept of some super-ordering power in all kinds of ways. He could, again, be satirical
But he
about it.
didn't believe in a divine...
No, he did not believe in the God of Abraham, Isaac, and Jacob, or of Jesus, or any, that God was not part of Einstein's lexicon, except to declare that it didn't exist. When a friend of his... Seriously, no, a friend of his...
And to you, I mean, listen, let's be honest, a lot of his best-known quotes have to do, though, with, God.
Well, yeah, but God in that metaphoric sense, or God in that sense to make his philosophical ideas, I think, palatable to wide audiences. He was a spiritual person. He believed in things that were larger than himself. But the thing that he believed in that was larger than himself was nature and the accessibility of nature's organization to human intellect. And that was extremely powerful for him. It moved him. He saw himself as seeking to be at one with nature and occasionally having these spiritual or transcendent experiences when he felt that. He wrote that in one of his travel diaries, contemplating the ocean, this kind of thing. But, attempting to shoehorn him into some picture of the scientist who really secretly believes in a traditional sense, no, that's not Einstein.
So let's conclude by asking the question. We're going to do a little moment at the end about the 100th anniversary of general relativity. But before we conclude, genius. Was he? I guess we can all agree about that, yes. But why? Why do you feel, Brian, let's start with you.
Well, I think the obvious answer that we would all give, but maybe I'll be proven wrong in 30 seconds, is that it was this remarkable union of all the things that we're talking about, right? So clearly there's something different about his brain. Presumably that had some role because the brain is where presumably all this stuff happened. But it was this wonderful confluence of his own personal history, of the kinds of open problems that were available for progress at that time, right? So it was the right moment for thinking about space and time and light. Maxwell had given us the equations of electricity and magnetism in the 1880s, right? So this is when Einstein is born and starting to think about things. So he's there at the right moment. He's got the right physical structure, and he's got the right attitude. He's got this perspective that I don't care what anybody thinks. I'm just going to go forward and understand the world. So you put all those three together, and at least for part of the time, you see what emerges.
Fred?
Well, he certainly was an incredibly hard worker. He had the infinite capacity to take pains. I agree, though, that he was a little bit of a lone wolf, and that may have helped him in the sense that when you're in that patent office making your living looking at inventions, you can't get to the university library because the hours were such that he basically was, a lot of his thinking was his own thinking, and he was not at that point in the academic establishment. And if you look at those original manuscripts in 1905, they're all handwritten out, and there's not a lot of references. Think of an academic submitting any kind of paper with no references or few references. Just doesn't happen. The referees would eat you alive. But Einstein, just the strength of his ideas and his independent thinking, untrammeled upon by external influences, maybe that did give him the focus to come up with that annus mirabilis in 1905. But one thing I would say, genius, it's not, it's not homogeneous. I mean, there are all sorts of geniuses. I mean, there's a guy on the basketball court who's got ball smarts. You got social geniuses. We call them politicians. Okay? So, I mean, he was, a physical genius. He was, in physics, a physics genius. I'm not going to tell you what I see on those photographs really explains that. He wasn't a great mathematician, but he learned enough math to take his strong suit, which is physics, and couch it in mathematical terms and make it demonstrable to the public, to the scientific public.
Tom, wind it up for us.
Well, I agree with what's been said by both Brian and Fred. If the word genius has any meaning at all, Einstein has to be on that list. He was a genius in his, the measure of it is his accomplishments. But I guess from where I sit, the point I keep coming back to is that the particulars of history matter. If Einstein had been born in Germany before 1800, he would have been before the Napoleonic, emancipation. He would, as a Jewish kid raised by a Jewish family from the villages of, South Germany, would never have come close to the education he needed to make the first step in any scientific career. So, a miss by 100 years. If Einstein had been born 30 years later, he would have been a very bright, good scientist, but he would have missed some of the window of opportunity that he went through so eagerly. And he might have gotten caught up, the particulars of history matter enormously to the ability of people with the capacity for genius to actually exercise it. Genius is not simply an internal characteristic of brain and smarts and talent and all that. It's those combined with circumstance, and the circumstances are social. We have geniuses because we have societies that are congenial to them at that time.
Fascinating. Well, all of you, I've learned so much, and thank you all, really, so much. I want to thank all of you for being such a great audience, and it is the 100th anniversary of relativity, so what's the science, world science
so the
going
Science
to do?
Festival will have that as a theme this year, so if you enjoyed this conversation, look for a variety of programs that will explore general relativity this May. So keep your eye out for those.
Thanks very much. That was great.
Thank you, guys. I learned a lot.
It was great. It was fun. Thank you.